Hello everyone. Today we will talk about database index and why we do not use hash map or binary search tree for a database index and why there is a need of a special data structure like B plus tree for an index. Okay, before moving on to other things, let's briefly understand what database index is. We talked about these in our previous video as well, but I'll give a brief overview uh, right now. So, usually the database has two types of files. One is index file, okay, and then there is a data file. So, data files hold the actual data, okay, of whatever application you are using. An index usually holds the index, which is essentially a key and an address which tells where this data is stored so that we could fetch that data quickly. So that's what index is. It is similar to index in a book where you have some term and then you have a page number, and if you want to find the term, you go to the term, search the term, you find the term, it gives you a page number, and then you go and open that page number. So that's a index in a book, and similarly we have a index in DB. Okay, so now we have covered the database index, and now let's see what a hash map is first. Okay, it's a in a simple terms, it's just a key value pair, right? Key value pair, and these are mostly in memory data structure, right? So they are in memory, and the lookup here is O of n. So you could get, if you know the key, you will get the value in O. Sorry, it's not O of n, it is constant. In a constant time you will get the result. O of n is in array actually, so not in a dictionary. Okay, so dictionary is constant, so it is really efficient when it is in memory, but on disk this doesn't work well for databases. We'll see this later. um, first let us see what a binary search tree is. So this is in memory right now. We have discussed, we'll try to discuss hash map on disk as well, like what does it look like on disk. Okay, so yeah, this sequential scan is on disk. We'll discuss this in some time. Now let's go on to binary search tree. Okay, so binary search tree is a kind of binary tree. I mean, it has every node has at most two children. Okay, and all the nodes which are less than the root are all to the left, and all the nodes which have a greater value are on the right. So this is not just for the root, but this is for all the nodes in a tree. So let's say I have to search 6 in this tree, so I'll go to 8. So all the search starts from the root node. I'll see, okay, 6 is less than 8, so I have to go left. Now I'm here, so now I'll compare 4 and 6. 6 is greater than 4, then I will go right. I came here, then I checked, okay, this is the one which I was looking for, so I have found it. So this is how the lookup works in binary search tree. And if we see the complexity of search in binary is on each question of yes or no, right? Whether it is on left or right, we are dividing it into two, and we are not searching half of it. and such pattern complexity for such patterns is log of n. Okay, base 2, but although it doesn't matter here because bases are constant operations, so we usually don't care, but it is big O of log n for this. And this is a tree which is height balanced. That means the height of tree on the left and to the right is equal here, but height balance trees, there's a the difference should not be more than 1 between left and right. In this, this is equal, but a binary tree could look like something like this also, which is not very balanced. So if you try to visualize, it is like this, and there are no nodes on the left of any of the node. So this is essentially a linked list. This is a type, if you see, it's similar to linked list, and search in these cases would lead to ON. So binary tree, when in worst cases, when they are not balanced, right, balanced well, so the search might take ON as well. So that's why BSTs are best when they are height balanced. Okay. So there are height balanced trees such as AVL, red black tree, which are height balanced binary search trees. Okay, let's go over a couple of things. Search. Okay, for 1,000,000 elements, we need 20 comparisons at least for these. Okay, so that's a lot of IO operations for a database. And if it is not height balance, ON. Okay, we have already talked about this thing. So while height balance tree solves a problem, like it's not always ON, so it would give you log of n complexity for searching a key, but then they are not great on disk. We'll see now, and this is the case for hash map also. So first thing is, if we could have entire data in the RAM, let's say, then we don't need anything. We could just use directly the RAM, but they are also volatile, so that is also one thing, right? So and if all the keys could be saved in RAM or hash map, hash map would be best case, where you would get a key in constant time, but we cannot even store all the keys in the RAM. So indexes needs to be saved on a disk, and there are a couple of issues with the binary search tree on disk and a hash map on disk. Okay, we will look at these in couple of minutes. So first, let's compare the speed difference, right? Speed from, if you see CPU L1 cache 1 nanosecond. So this is a comparison. So fastest is L1 cache, RAM, NVMe SSD, mechanical SSD. It has a head and a spinning disk. So if you see, compare, right, it is 1 second to like 4 months, which is huge difference. Even NVMe would also take 3 to 30 hours, right? So this is the speed which we can fetch the data from these devices. So that's why we try to optimize that. Okay, we should be getting the best for cache, RAM, so that we can fetch faster, right? So the fan out, which is number of child pointers for BST, it's just 2, and there are other data structures like B plus, which could have huge fan out. I mean, number of children, hundreds of children it could have. Okay, so for million records, it will be 20 levels deep BST. And here is the main problem with why we cannot use BST. So let's say let's talk about hash map first. So let's say you have saved the hash map on the disk, okay, and it has keys, lot of keys and values, and you have to search some key 56. Okay, since this is not in memory, right, this is on the disk, so this, a part of it needs to be brought to memory, and then you can do an operation on it. So there's something known as page. So that's the minimum you can read and write from a disk. So this is different from OS page. Let's not confuse this with OS page. This you can call it disk page or DB pages, right? Postgres use 8 KB. They are 4 to 16 KB in size. Okay, so you can only read one or multiple pages at a time, right? So if you have a key value stored on a disk, and let's say one key is coming in one page for simplicity. So you pick up one key, bring it to memory and see, oh, this isn't matching. You go to another key. Okay, you bring it to the memory and then you say, oh, this is also not matching. You go to the third, because the entire index cannot be brought into memory. That's why we have this on disk. So similarly, this becomes a ON thing, kind of, right? You're checking one by one, and then these can lead to number of operations can be huge, right? Like for 1 million records for BST, it will be same thing, right? 20 operations we are doing. In BST also, these nodes are not stored sequentially one after the other. This could be a random access, and each random access would have a different IO operation. Okay, so because of that, if it would have been great if this number and this number are in the same page, but that not might be the case with the BST, because they are like pointers. They use pointers from one address to another, so these could be random, and if they are random for 1 million elements, you will have 20 comparisons. That means 20 IO operations, and IO operations bring latency. HDDs, especially HDDs, even for NVMe and other, but these are pretty slow because they have a mechanical head, and then you have that head needs to go to that sector and pull in that particular page. So and for billion it would be across 30 operations, I think. So that's why we cannot use BST because the operations are huge, or any kind of hash map on disk for index of a database, right? This is one thing. Another thing is when OS loads the entire database page, which is 4 to 16 KB, okay, very small amount of it is used. Let's look at the example. So when the page is fetched, right, so if this is the size of the page, very small amount would be the key, and rest everything is waste. But you have to pull it in main memory because that's the minimum unit you can read from the disk, right? So that is the minimum you'll have to fetch. So let's say your disk page size is 4 KB, which is these many bytes, okay, and then you have BST which will come around 24 let's say 24 bytes, but rounded to 32 because it has 2 pointers and 1 value. So if you have 8 bytes, then you will have 8 into 3, that will be 24. But for rounding stuff we are using 32. Okay, so let's say 32 byte approx. Then if you see utilization, right, out of 4096 bytes in a complete page, we only need 32. Like, we are utilizing only 32. The rest of the space we are not using it, but we still have to do that operation and bring it into memory. So that's a kind of waste. So wastage is here 99.22%, right? So that is another thing, that there's a huge waste of I mean, there is a IO operation, large IO operation, and out of that also we are not using all the values we get in the main memory. And to tackle all this, we have another kind of, trees, which are B plus. First is a B tree, and then B plus trees are, more powerful. And then we will discuss these B plus trees and how they overcome both the problems. One is the number of operations, another is the page thing, wasting of the memory what we bring into the RAM. So we'll discuss this in a next video. Until then, bye bye, take care.